calculating the pH of a strong acid is a piece of cake. Strong acid's fully ionized, so if you had a 1 molar solution of a strong acid, it'll give you 1 mole of hydrogen ions. That's all I need in order to calculate pH. Eventually, pH is opposite log of the hydrogen or hydronium ion concentration. The problem with a weak acid is that it does not fully ionize. So just because I have a 1 molar solution of weak acid doesn't mean that I'm going to get 1 mole of hydrogen. But that's what I need in order to calculate pH. I need the concentration of hydrogen or hydronium. So we're going to have to approach it from a different angle. So let's check out this one. We want to calculate the pH of a 1 molar hydrofluoric acid solution. Well, first of all, I know that it's an acid because I'm given a Ka value. And second, I know it's a weak acid because that Ka is small. It's less than 1. I'm going to have to use that equilibrium constant to figure out the amount of hydrogen that's really formed from this HF molecule in solution. So we're going to approach it with an ice table. I mean, any equilibrium problem, right? I mean, if we're lost and confused, let's just try an ice table. So I think the hardest part of all of this is getting the initial equation. So I'm going to have my weak acid, HF, hydrofluoric. It is in solution, which means water is present. And so now the definition of an acid is a hydrogen donor. So the HF is going to donate a hydrogen, and that really negative electronegative oxygen on water is going to be the hydrogen acceptor. It'll act like the base. So we've got our acid, and water is going to act like the base. So on the product side, I'll be left with the fluorine ion and H3O+. So on the product side, that fluorine ion is my conjugate base. It'll be attracted to hydrogen, or if this were to go in reverse, the fluorine would pick up the hydrogen. And then H3O is my conjugate acid. Often on the product side, if you've got a positive ion, it's probably positive because it's got an extra hydrogen. So in the reverse, it would be the hydrogen donor. There, that's the worst part, getting the balanced equation. Now, technically, this is an aqueous solution. Water is a liquid, and these ions are also aqueous. All right, so let's try setting up an ice table, and then we'll see where this takes us. I do have the initial amount or initial concentration of that acid, 1 molar. Now, technically, in equilibrium expressions, we don't use pure liquids or solids. So I don't really care how much water is present. I'm not going to use it anyways. It's in my equation, but I don't really need it for any final calculations. So I'm going to keep it in the equation, but I'll just kind of scratch it out of my ice table. Initially, we're going to say the product ions are 0. And what we want to know is how far forward will this shift? Now, I know I can't have zeros at equilibrium, so we're going to shift forward, and we'll just call it X. So some of that HF will dissociate. We'll form some fluorine and some hydronium. So that at equilibrium, this is 1 minus X, X, and X. And really, the X value that I want to solve for is this guy, right? This is what I need in order to calculate pH. So once I get X, that will be the concentration of the hydronium ion. Then I can go opposite log, game over. We just need to solve for X then, right? But that's okay because I have the constant. Ka is 7.2 times 10 to the negative 4th. That equals products. So X times X over reactants. 1 minus X. All right, so let's just solve for x and we're good, right? Yeah, I don't know if I really feel like working that hard. I'm gonna have to cross multiply and kind of simplify, and I mean, I think I'm gonna end up needing the quadratic equation, and it might be fun, but I don't know if I really want to spend my time on that. And so back in the day, we mentioned that there's this shortcut called the 5% rule. Now at the time, we didn't really use it much because we said that it really only applies when you have a small equilibrium constant, which we do with weak acids and bases. It's one of the best times to use this 5% rule shortcut. It really says this, that if your K value is so small, yeah, we're shifting forward, but we're not going to shift forward by much, which means then that X is really small. And maybe X ends up being so small that 1 minus X, maybe that minus X is kind of insignificant. I mean, I'm expecting X to be really tiny, that this isn't going forward by much. And so let's kind of ignore the minus X, which just makes your math a lot quicker, because now all I need to do is cross multiply, which I feel like I can do that. Cross multiply, and then we'll take the square root. So I'll have something like, well, 7.2 times 10 to the negative 4th times 1 equals x times x, or x squared. So much quicker, right? I mean, nothing against the quadratic equation and FOIL and all that good stuff, but this is so much faster. I've got better things to do today. So I'm going to take the square root of each side. X equals about 0.0268. And now technically, if I wanted to check the 5% rule, I would take that X value and say 1 minus X equals whatever. And then I would just make sure that that doesn't differ from the original assumption 1 by more than 5%, which, yeah, I mean, it's going to be what, like 0.9 something? I mean, it's going to be really, really close. And so I don't even check the 5% rule. I just know that with weak acids and bases, it's always going to work, because the only other option then, if the 5% rule didn't work, you'd have to use the quadratic equation to solve for X. And on the AP exam, you will not need to do that. The AP exam can be solved with just a simple scientific calculator. You don't need it to graph or do anything fancy like that. So the 5% rule always works. Awesome. So I think we're ready to rock this thing now. We've got X. X is the concentration of hydrogen, which is what I want to use to solve for pH. So I'll just say that pH is opposite log of 0.0268 molar hydrogen or hydronium. Plug it all in, and I'm looking at about like a 1.57. And there she is. Again, the big picture kind of makes some sense, right? That like equilibrium and ice tables could be used to solve for the amount of hydrogen, as long as I have the K value, that I know it's going to shift forward and produce some hydrogen, but it's just not going to shift completely. So we have to solve for X. Once I have X, I'm off to the races. Then X will be the amount of hydrogen or hydronium, and I can go opposite log. Now, if you want, you could pause and try this hypochlorous acid example on your own, or feel free to walk through one more together. All right, so let's start with an ice table. Now they've got hypochlorous acid. All right, they're not giving me the formula of this thing, but you could have just called it HA and some general weak acid, or technically it is HClO, hypochlorous acid. The thing reacts with water in solution. It is a hydrogen donor, so we'll be left with the hypochlorite ion and hydronium, H3O+. And so after a while, we'll find that a lot of these balanced equations are all really similar. And in the AP packet, sometimes they do just kind of use this general generic equation for like any acid. They'll say HA, where H is hydrogen, A is just whatever the conjugate base is, and then this would be listed as A minus, the conjugate base. All right, let's do this. Ice table. These things end up being like all solved the same way. So once you do a couple of them, you'll get really good at it. I know you'll do really well on this. We have the initial concentration, 0.1. I have water, but I'm not going to use it. So it's in the equation, but I'm just going to kind of scratch it. Initially, the two ions are 0. It's got to shift forward, but I don't know how much. So we'll call it X. All right, so that at equilibrium, this is 0.1 minus X, X, and X. All of these ice tables are really, really similar. And in fact, you might get so good at this that after you practice a few, you'll say, please, these all look really similar. I might not even need an ice table. I do need a K value though. My Ka is 3.5 times 10 to the negative 8. That's tiny. My acid dissociation constant. But now, can you kind of see the similarities in these two ice tables? It's always going to be like X times X on the top in the numerator, or X squared, all over the initial molarity, 0.1 minus X. And we're always going to apply the 5% rule. So whatever X is, it's going to be crazy, crazy tiny. And that K value is super tiny. So I'm going to ignore it. And I'll just assume that I can probably just say that the concentration of the original acid is really close to its initial. It makes my math so much quicker. I'm going to cross multiply and take the square root. Awesome. Okay, so then I got my 3.5 times 10 to the negative 8. Cross multiply times 0.1. Well, that's easy, right? That's just my 3.5 times 10 to the negative 9. And that equals X squared. So I can just take the square root and bingo. I'm looking at about maybe 5.92 times 10 to the negative 5th. And now I do just kind of look at my X value to make sure that it comes out to be something small. It should be small because we're not going to shift forward by much. That X is tiny. So yeah, the 5% rule was a totally valid assumption. Now I'm ready for pH. Of anything in the ice table, the only particle that I really care about is that hydronium ion. And that equals X. So my pH then is just opposite log of 5.92 times 10 to the negative 5th. The concentration of the hydronium ion. My pH then is about 4.23. Now I obviously also check at the end to make sure my pH comes out to be something less than 7. So yeah, this seems pretty legit. So can you kind of see that there's a lot of similarities in these weak acid ice tables? I mean, the only thing that's going to be different is the initial concentration and the value of the Ka. But otherwise, they're all set up exactly the same.